who's all here? Uh-oh, we got Hacker Man still going in the background. Let's see if we can reset Hacker Man right here. Who's all here? Got to reset Hacker Man. Resetting. Should go, hey, what's up, Jackson? Good to see you. What are you working on? Should reset Hacker Man. Hacker Man doesn't reset itself these days. What's going on with Hacker Man? Good to see you, Jackson. Got myself playing in the background right there. Let me see if anything crazy is going on in the world. Notification. Ah, too funny. So sweet. Oh, it's too funny. I saw something retweet by one of my colleagues. It's too funny. Oh my gosh. We gotta. Oh my gosh. Oh, so many craziness. What's going on? Ah, so much going on. If you're here and you have questions, let us know. I'm just looking through the world today. Checking out the world today. See what's going on. Yeah. If you have questions, let me know. I'm just chilling out at the moment. What are you working on, Jackson? We can work on some stuff. Yeah, chapter 7 quiz, let's do it. I'm just like, Mountain Dew Energy Code Red. Oh no. Oh no. Okay. I'm gonna get serious right here. Mountain Dew Energy Code Red. I saw something I shouldn't see right there. I am not allowed to drink that. Wait. I'm literally gonna send this to a friend of mine. Where's that at again? Let me go see that. I'm gonna send this real quick to a friend of mine. Okay. I got the quiz getting pulled up right here. Chapter 7 quiz. Let's go do some questions from it. We had our fun. We're relaxing. It's a Monday. Chapter 7 quiz coming up right here. Let's see what my friend thinks of that. Okay. Let's take a look. Here we go. The manager of a bookstore. The manager of a bookstore. We're going to put on our serious face right here. 515, Stat 201, Chapter 7 quiz. Chapter 7 quiz. Bookstore manager. Okay. The manager at a bookstore wants to predict the number from sales of people working using the accompanying data. So they're going to have people working in sales, number of people working in the sales in thousands of dollars. And then they give other units like the mean of the Y, which is the average amount sold. So that's the average numbers there. The standard deviation of the Y variable. The R, which is the correlation. Breakfast cereal important? Yeah, we'll do breakfast cereal next. You got it. And then the X right here is the mean of the X variables, which is the number of people working. And the standard deviation is the variation. So what you want to do if you get a question like this is have jump open. So you want to go to jump and go to File, New Data Table. This is the number one way to solve these, I believe, is to use jump and to have a new data table open. Don't click inside of it anywhere, but go to the data sheet right here, click right here on the data table, click right here and go to Copy to Clipboard. Once you've clicked Copy to Clipboard, go ahead and hit Control or Command C. That will copy the data into your onto your clipboard right there. And now go to Edit and Paste with column names. This is ever important that you paste with column names. If nothing pastes, it means you didn't copy it. So make sure you paste with column names and you'll see the data here. Alternatively, you can write the numbers, but you want to make sure they're blue. If the numbers are not blue, that means you have categorical data. This is wrong over here because the first row has the column names. Don't try to fix it because you'll have to change a lot to fix it. It's better to just start over and paste with column names and they'll be blue. That was edit, paste with column names. Make sure to do that and make sure they're blue. There you go. So with this right here, we have the number of people working and the number of sales. Let's go here to Analyze Fit Y by X. This is Analyze Fit Y by X to do a bivariate relationship, which is where we get the scatter plot. We want to predict the sales in thousands of dollars from the number of people working, which is the X variable of interest. So we have the number of people working is what is going to explain our sales, which is why do we have certain sales. Always try to say it that way. Well, maybe the number of people working explains why we have certain sales. This is what we're interested in. Why is this happening? This is what explains it, the number of people working. When you do this, you will get the scatter plot right here, which this shows a really good linear relationship when you look at it. The slope's going to be positive. It almost looks 1-to-1-ish, not quite. Maybe it's a little, let's see, this starts here at about 4, and then at the end it's here. It looks about 1-to-1. The slope looks to be about 1 or something, or 0.8. Let's fit the line. Go to the red arrow, fit the line. The slope is 0.8, so a pretty good guess. It looked about 1-to-1 relationship, so I was kind of visually looking at it. Residual's got a little bit of weirdness, but the slope of the line is found as under the estimate of the slope. And so a few spots to know to look at in this output. When you're looking at this output right here, you want to know that the slope is going to be B1. It's also the estimate of the slope. That's B1, that's B0. The estimate of the intercept is B0. So the intercept is right here. And so this is Y hat, which is the predicted sales in thousands of dollars, is equal to the intercept, which is B0 in notation, plus B1. And this is the value of X, or value of B1 right there. And then X is just called number of people working, which you see down here. Very important to know to connect the output right here and see understand what you're seeing. So it wants to know the value of the slope. Well, the value of the slope is just this. That's what it is, round to 3 decimals. There you go, rounded to 3 decimals. Next, it asks us, what does this mean? It's for each 1 unit increase in number of people working, we expect the sales in thousands of dollars to increase by 1,000 units. Know how to write that out. At the end of our class, we were practicing writing these things down, so we should see something similar. This means on average that an additional increase of B1, that is true. These look right. B1 times thousands of sales. Oof. Oh, how did they write this? They wrote such a weird way of it. This means on average an additional increase of B1 in sales, that is, and we probably want the dollars there, is associated with one additional salesperson working. That sounds correct right there. That's really weird. Don't like the way they wrote it. I would write for each additional person working, we would expect an increase. Is there a way to solve this without jump? Yes, but it's a lot more work. The way to solve this without jump, I need the chapter 7 notes. If you want to solve this without jump, you could use the regression solver too. I made the regression solver, but you could also use the notes over here. I'm going to show you in 2 seconds. You could use the notes on how to find the slope and how to find the intercept. Not that bad. You could just solve this equation right here and get the slope and the intercept. So it does give you the values of R, which is correlation, standard deviation, which is S sub Y, standard deviation of the Y variable, standard deviation of the X variable, and there is the mean of the X, and there's the mean of the Y. So I think they're really going towards, it wouldn't be that bad. You'd just be solving the equations. I prefer to visualize it, and also on the test, you'll see the output. So there's all those values. S sub Y right there is standard deviation of Y. Y bar is mean of Y variable. So you could solve it without using jump. It's a little more algebra than interpreting output, which is what we try to focus on. Find the intercept, so you could solve it. I prefer to use jump. We won't have you solve those equations on the test, so I prefer to know where in the jump output the intercept is, which is kind of more test relevant. So the reason I do it this way is because on the test, you might have to know how to look at jump output and say, well, the equation is B0 plus B1 X. So there's the B0 right there. B0 is the first number we have, which is also the estimate. You see how that's under estimate in this column of the intercept if you go that way. So just very important to know how to read the jump output and understand what you're seeing there visually. What does the intercept mean? It's the value when we have 0 workers, the expected predicted price. So, or sales, excuse me. We expect when 0 people are working for sales to equal $9,074,000. But you can't have 0 people working. You wouldn't have your bookstore open. So that's a little illogical. It means that on average, the total sales will equal by the number of, nope. It means on average an additional, no. It means on average, the expected sales is B0 exactly times 1,000 with 0 salespeople working. It does not make sense because it is unlikely that any sales would be made with 0 people working. Very similar to what I said right there. Very similar. Very, very similar. Write down the equation. So at this point, you literally just want to take the B0 and put the B0 there and the B1 and put the B1 there. Did I grab the right? Yeah, it is 9.08. And then check your work by looking at the equation itself and seeing that you have the same equation written right there. I think that'll bear it. There it goes. So make sure, and it wants to 3 decimals, 9.074. That is correct. And then plus 0.878. And there it is right there. Now we're going to use the regression model to make predictions where we just plug in the value of X right here with 15. So now let's take right here, 15 times that, and then add to it the intercept. I usually add the intercept after because the intercept could be negative. There we go. And now let's plug in the value to the nearest tenth. Okay, it wants me to delete my decimals. If the sales are actually $23,000, oh, round to the nearest $10 is needed. Okay, but here's the thing. It's in thousands of dollars. Round to the nearest $10. We would have gotten this one wrong because it wants rounded to the nearest $10. That's weird. Don't like that it's doing that. Can you remember how to insert data in jump again? Yeah, we'll do it at the end of that. We'll circle back and we'll put data back into jump. So now it wants the residual. So we're almost done with this. And let's take a look right here. So the predicted sales is what comes from the model. So predicted sales is from the model. So this is the predicted, which means the model itself is where we see the predicted. The actual sales is going to be the dot. And the dot is over here at 23K. The predicted sales are below that at 22.24K. And so that's the predicted. Now, what we see right here as the distance they are away is going to be the residual. So that is the residual. The residual is the actual minus the predicted, and it wants the nearest tens of dollars. So now when we take the difference right here, we would see that the difference subtracting them is $760, I believe. $760. And let's check our math. There's the value, but we're going to round it to, there's the actual minus the predicted. I forgot a 2 right there. That's a lot of 2s. There it is, 760. So 760 is the distance those points are away. And we'll put the data back into jump here in a second. Has the original estimate for part F over or underestimated the sales? So when we look at this visually, it underestimated. The model is underneath. So let's go to the black pen right here, and we've underestimated. The model gives the predictions, and this is an underestimate of the sales. We underestimated them. And that should do it. Should be correct. Boom, got that 100. Get a little worried with those long, long questions. So how to get data into jump? Here are the steps. You ready, Blake? Or Jackson right there? We click right here, and then go to copy to clipboard. Are you good on this? Give me a Y or N in the chat. Like if you're good on this part, type Y. If you're not good, type N, and we'll restart. But you go to this part where you go to copy to clipboard. So this will just put it to your clipboard right here. So give a Y or N in the chat, like Y you're good. And okay, now you copy to clipboard and you hit Control or Command C. Control or Command C. I'm on a PC, so I'm hitting Control C. If you're on a Mac, hit Command V. So Control C or Command C, sorry, C for copy. Now that you've copied it, we're going to go over here to Jump. Inside of Jump, you want to go to a new data table. Go to File, New Data Table. That's file, new, data table. Also control N or command N will do that. File, new, data table. File, new, data table. Once you are inside the new data table, don't click anywhere. Don't click anywhere yet. Go to edit and then paste with column names. Edit, paste with column names. So once you edit, paste with column names, there you go. Did that work, Jackson? Let me know if everything went perfectly. Got it all in there, because now you can analyze the data with analyze fit y by x, and then it's pretty quick from there. But that's got it. How are we looking? How are we looking? We'll do that breakfast cereal one here. Thank you so much for being here, Jackson. We're just chilling out. Getting some work done. Breakfast cereal. Where's the breakfast cereal? Breakfast cereal's an important part. There you go. Is it this one? Got it. Nice job, Jackson. Let's throw you 1,000 points right there, and let's do this breakfast cereal question. Okay, time for the breakfast cereal question. 1,000 points, Jackson. Okay, for many people, breakfast cereal is an important source of fiber of their day. Cereals are often contain potassium, a mineral shown to be associated with maintaining a healthy blood pressure. An analysis of the amount of fiber in the grams and potassium in milligrams in 77 breakfast cereals is produced. The following regression model. Predicted potassium, that's what the hat means above it. Predicted potassium is equal to 37, which is the intercept, plus 26, which is the slope, times fiber, which is the x. If your cereal provides 10 grams of fiber per serving, how much potassium does the model estimate or predict you'll get? What do we need to do with this model now? What do we need to do? We have right here a proposed value of x. So what should we do? Plug the value of x in. It just wants you to make predictions with the model. If it actually has 300, so here's a follow-up. If it actually has 300, what is the residual? If it actually had 300 grams of potassium, what would be the residual? Mine was different. I think there's another one we'll do next. If it actually, so Jackson, if it actually has 300 grams of potassium, what is the residual? If it actually has 300 grams of potassium, what would the residual be? If it actually had 300, just a follow-up question. So if it actually had 300, so we predict 297. We predict 297, but it actually... Three. Yep. It's 3 away. So we don't usually put I should put where that's on the model, but it's 3 higher than it was predicted to be. Does that make sense? So the residual of 3 means we were off by 3. Exactly. Actual minus predicted. Jackson, great job right there. And then just sometimes people reverse it. Doing the drawing can help too, like to show that it would be above the model. Like it actually has this. It was predicted to have this. It's above the line. So anything above the model, this is the positive residual region. This is the negative residual region. If it points down here, it has a negative residual. So the distance, it's below the model. So the model under or overestimated. Last one here, then we're going to do yours. The model, the point we're currently talking about on the screen, the model under or overestimated it. A lot of questions have been saying that, so that's why I'm reviewing it. The model under or overestimated? It underestimated. Jackson, you're doing great right here. Good practice. It underestimated it, and then drawing it out right here can really help. So when there's a positive residual, the model's underneath it, so the model would underestimate, and you can see that here visually. Really great job. Here we'll do the next. I think there, as you said, there's another version of this. So here's the, we'll find it. Good practice. Oh, here's the next version. You ready? Version 2. So let's get version 2 of this question. We're going to knock out a lot of questions here. Stat 201. Version 2 of the question. Oh my gosh. There we go. V2. Here we go. So this version says to us the same sort of stuff, gives the same sort of model. Important to first notice the what and the what of the model. Like when you see a regression model like this is going to be the main important stuff for us to think about. What is the main important things to notice right here and right here very quickly? The value of the what and the what instantaneously. Like this is what my eyes are drawn to when I see a problem like this. I say, that's the regression model. I have a what and I have a what. We want to see those things and immediately be like, that's the this, that's the this. So that's when you get a regression model, you'll be like, ooh, I have two things right there. I have a what and a what. B0, B1, slope intercept. Yep. Notation, brother. So the intercept is exactly intercept and slope respectively, exactly. So the intercept is B0, it's when x is equal to 0. B1 is for each 1 unit increase in x, which is B1, the slope coefficient. So coefficient just means value, like a number, the number of the slope, coefficient, value. We use weird words sometimes. So the first question asks, choose the correct answer below. The serial is an outlier. Oh, wait. So you might have a different question. Okay. From this model, you can estimate a serial's potassium. In this context, what does it mean to say that a serial has a negative residual? Okay, let's look at that. Negative residual means it really, so we're predicting potassium. So the predicted potassium, Y hat right here, if there's a negative residual, oh my gosh, I gotta turn off those messages. Gotta learn how to turn them off. Negative residual means the point is down there. Negative residual means the point is down there. So what does that mean? What does it mean that has a negative residual? It means that its actual potassium is what? Like negative residual means it's below the this. So a negative residual means what? Like don't worry about the answers on the screen. What is higher? Like you just, if you finish, you got it right there. Negative residual would mean what? Like something is higher. That is true. So go a little more detail and we'll find the right answer. Well, no, so this will be the actual down here. The actual is lower than what we predicted. So the actual potassium is lower than predicted. The model overestimates. So the model's above it. So the actual is below. Does that make sense? So a negative residual, and you could just assign fake values to this, like 10 and 4. So what would be, yeah, the red dot's the actual, exactly. The line is the line of prediction. So the line makes predictions. So the residual here would be what? Does that make sense to say the model is, or the predicted is 6 higher than the actual, or the actual is 6 lower than the predicted? So when you talk about it, the negative residual means the actual is below. So let's see if something confirms that sort of idea right here. The serial, no, it's not really an outlier. The potassium content is actually higher. No, the potassium content is actually lower than the model predicts. And so that's got it right there. Whoops. Wait, was that the... Okay, yeah. Wait, what? I'm so confused. Check answer. Is there another one that's just like a little tiny question right here? Oh my gosh, so much on cereal. It really cares about cereal. Analysis of the 500 gram cereal and potassium and serving 77 cereal contents. Explain what the slope means. So what does the slope mean? This is like the most partial question I've ever seen. Little bits. So what does the slope mean? It's what? For each what? What does the slope mean? The slope is what? For each 1 unit increase in what? And look at the variable it's associated with. It's C is the answer. The slope is for each 1 unit increase in x. So you want to be able to interpret this. You ready? Try to do this without, if you're watching this right now and you're seeing the answer, try to do this without looking at the answers here to say, for each 1 unit increase in fiber in grams, we would expect the potassium of cereal to increase by 29 units of potassium on average. So let's see right here to see what we have. The model predicts, and there's the 29, which is the slope coefficient. The model predicts that the cereal will have approximately 29 more milligrams of potassium for every additional increase in fiber. So as for each 1 unit increase in fiber, we expect the potassium to increase by the slope coefficient. So it's a rewording of my answer right there. For each 1 unit increase in fiber, which is the x variable, so for each 1 unit increase in x, we expect y to increase by b1 units. There's ways to reword it, but I like to go with a strong structure. That way you don't make errors when you get to the test. For each 1 unit increase in x, we expect y to increase by b1. For each 1 unit increase in fiber, we expect potassium to increase by 29 grams. There you go. And they've reworded it a little bit. Do we have more breakfast cereal to talk about? Maybe the Intercept? See if there's any other breakfast cereal questions. Which other ones are you wondering about, Blake? We got a bunch of questions. No, Jackson, sorry. I was talking to Blake and Evan or Ethan. What other questions are you wondering about? We still got. I'm gonna go till what time your time? 1:55 your time. Some residual plots right there. Which other questions are you wondering about? Let me know. We did a few of these during office hours today, but ooh, that's interesting. Look at that. That's a non-linear. I might do this one. This is a new one. This one's interesting. Tell me one, Jackson, if you want. I'll do any others you want, but let's check out this one right here in the meantime. Analysis. Oh, yeah, let's do it. Analysis of the relationship between fuel economy. I saw it a moment ago. You got most of this done. See, a lot of them are similar. A lot of them are very similar, and you'll notice that it's a lot of like checking of knowledge of the same sort of things. Here we go. Oh, oof, a lot of stuff to write out right here. So let's try to do this as we talk over this question. Let's talk about. I think I can do it. Yeah, of course. Thank you. That's what we're here to do. No, this is like I'm so glad you're here because I want people here to do practice. It's a different one. Okay, then we'll do this one and then we'll do the next one. The relationship. We'll call it version 1. Okay, so let's do this one, then we'll do the next one. And let's look over what it wants us to learn right here. So it looks like they're giving the model, which is the y hat. Then they give you the b0 and the b1. Explain what the slope means. So they just want to know the slope coefficient right here, which is going to be b1. So it's a good problem for identifying what the slope coefficient is. So you need to know your regression notation for this problem. Y hat equals b0, which is the intercept, plus b1x. So they're asking specifically, what does the coefficient of the slope mean right here? So it's for each 1 unit increase in x. So do you want me to say it again? For each 1 unit increase in x, we expect y to increase by b1 on average. So for each 1 unit increase in displacement, we expect the combined miles per gallon to decrease, because it's negative slope, decrease by 3.315 on average. So we've got to make sure we do that because they're kind of pointing to that down here. The car estimates that a car will lose. So these are the two in between right now. The model estimates that cars lose an average of this many, yes, for every additional liter of engine size. That's the displacement right there. Someone told me that a while ago. 3.3. A little bit of car knowledge needed right there, but at least miles per gallon is what we're predicting, and that's the Y. So for each 1 unit increase in engine size, which is displacement, we predict the car will decrease its mile per gallon by 3.315. Got the numbers right. Oh, there goes. Not. I thought the negative. I forgot for a moment, but good. A little tricky. A lot to pick from, but making sure you know it's a negative slope and know the XY relationship. Decent, but be able to write those out. Analysis of here we go. Here's the next one. Here's the version 2. Look at all the questions we're getting done. Good stuff. Let's knock out this next question right here. And so with this, version 2 of this question, what does it want us to know? You ready? Analysis of the relationship between the fuel economy and engine size, liters for a 35 models of cars, produce the regression equation, miles per gallon, all this good stuff right here. So we're predicting miles per gallon. If a car has a 5-liter engine, what does the model suggest the gas mileage would be? So what do we do right here, Jackson? They want to know that you can do what? Yep. That's it, Jackson. Great job. Excellent work. Some points in the chat. Just plug in the value of X, and that's all you're doing right here. So we're going to take the value of x, which is engine size 5. Just plug that in. Make sure to carry all decimals till the end. So you go 5 times 3.829. Now be careful, that's a subtracting. So 36.24 minus that value. I saved it for a moment. Just make sure it makes sense. Like double check your work, but double check it all. Like write it down, check it out, make sure it works. 17.095. So now that we have that number, round to 1 decimal, that will round up right there, and we should get it right. Check that answer. Good to go. Now this car actually has 15. It actually, let's just do a fake thing right here. It's predicted to get that many miles per gallon, but it actually gets, is another check your knowledge, it actually gets 15. What's its residual? So I'll draw the model for you right here, what it looks like visually. What is its residual? So it actually gets 15, and it was predicted to get 17. Not looking good. 17.1 rather. And it actually gets 15. What is its residual? So the residual is how much you miss by. So think actual minus predicted. Just all these follow-up questions to be like, oh, I know what a residual is. I know how to use it. And that's just like a hypothetical, like, well, we predicted it would get 17.1. It actually gets 15. Careful. I did this one for this reason. Jackson, good work right there. We're going to 3,000 points. So look where it's at. Look where the point's at. This is good review. That's why I do these things. Good follow-up. 1,000 points, Jackson. So, wait. You're close. But wait, look where it's at. It's not going to be 2.1. 2.1 would be that car. That car would be a residual of 2.1. And that car right there, that car is at 19.2. Negative. Because the residual tells us how far above or below the line is. So this is 2.1 above the line, and this is 2.1 below the line. Does that make sense? So the car that is at 15 actually has a residual of negative 2.1 because it's 2.1 below its predicted value. The car that is at 19.2 has a residual of 2.1 positive, you can say 2.1, because it's 2.1 above its prediction. So the residual tells us how far the actual is above or below the predicted. So when the residual is positive, the actual is above. When the residual is negative, the actual is below. So residuals are how much we miss by. And just remember, it's like your predicted and then how far away your actual is. So if the residual is positive, the actual is going to be higher. If the residual is negative, the actual is going to be lower. The dot is where the actual is. Like that is what that car actually gets. Like if you measured that car and looked at it, it actually got this. If you didn't look at it and you just made a prediction and said, I think it's going to get this, that's your prediction from the line using the model. So the model makes predictions for us, and the actual is what it truly is, what it actually is. That's why I call it the actual, or sometimes it's called the observed. Like you observe it getting that, you look at it and it actually is that. So that's why I say actual. I like to use actual, then I can say residual equals actual minus predicted. So if you didn't know it, residual equals actual minus predicted, and the notation for that is the residual, which is E, is equal to the actual minus the predicted right there. E is residual, Y is actual, and P is predicted. So these points are the actual, the Y's, and then the line is the Y hats, and then the distance is the residual E. Good stuff right there. Good practice. What other ones, Jackson? Let me know. You might be knocking out the whole quiz right now. We still got like 25, 27 minutes. Gonna do a meeting. I got multiple meetings today. Busy day. Which other ones should we do? Look at all this that we've done so far. Well, we got the start of it done. We just knocked out that one. Tell what each of the results to the right indicates about the appropriate... I saw that down here on 12, right? Maybe it's 13? Yeah, there it is. I knew I saw it around there. Okay, cool. These are fun. There's two versions of these. So let's do both. These are really good questions. Residual plots. So a residual plot is a plot that is used as a diagnostic plot to analyze a regression. So a residual plot is a follow-up to a regression. So we talked about that a lot today. Here's our notes from today. As we looked through residual plots, and to make a residual plot, you literally take your model, right? Here's your model, and you make it flat. Look at that weird little shark creature right there. A residual plot is a follow-up. We call it a diagnostic plot. A lot of times we look at it for things like plot thickening to see if there's a plot thickening issue. So all you're doing is taking your original data and making it flat to do another diagnostic. You see lots of residual plots through here, and a big way to know it's a residual plot is you will see that it's set to 0. It'll say residuals. So you want to look for key things like that where it says residual, set to 0, and there's a line. So these do a decent job. It does say residuals right there. Now they would have a line going through the center of them. And what do you want to see in a residual plot? We got multiple people in class who know the answer to this. What do you want to see in a residual plot? What do you want to see in a residual plot? Residual plots are the leftover variation. Residual plots should show what? Know this, which looks like one right there. Residual plots should show know this. And the fourth condition, the plot doesn't thicken, is going to be a condition that's really well checked by residual plots. So what do you think? Residual plots should show no patterns. They should show nothing. I know this might sound crazy, but a good residual plot would look the following way. No pattern, Jackson. Nice job right there. A good residual plot looks random. That is a good residual plot. It would come from a model. This is the model it came from because it's just the line flat. Or we could just take this and bend that line. Watch this. Let's go to our cut. And we're going to take this, and hypothetically speaking, that residual plot right here, hypothetically speaking, could have came from a model that looked something like this. And sometimes it's even tighter, like it might, the residual plot fans it out. So there you go. That is the exact same scatter points. That's how residual plots work. It's the exact same points, but it's the line flat. And you set the line equal to 0 because anything like this point right here, that point right there, that's on the line right there, that point has a residual of 0 because we can now tell it's a vertical distance above or below the line, where these are the positive residuals and these are the negative residuals, and then points on the line would have a residual 0. That's the point of a residual plot. And a lot of times it's zoomed in so you can get a better idea of what's going on with the pattern in the data. So we get a residual plot. I did a bunch of these earlier, and I think I still have one of them up that really shows this. This was a problem we did earlier, and here's the data. It's very hard to see this, but there's a big problem with this data with the non-linear relationship. So this is the residual plot right here, the one we use. There's multiple ways to do residual plots, but this is the one we talk about in class, is where the line is made flat, and then you can look at the residuals and take a look. It's very hard to see that there's a curved relationship in this data, even if I help the y-axis right here. You really can't see. You can see a little bit of the curve, but the residual plot will show you that. It'll also show you a fanning out of the points. So plot doesn't thicken is a really good thing to check with residual plots. Speaking of plot doesn't thicken, here you go. First one, the model is actually getting stronger because the points are going closer to the line. So the fan pattern indicates that the linear model is not appropriate. The model's power increases because it's getting stronger. The tighter the points are, the stronger it is. The model is increasing in power as it goes across here. So if it gets tight, if it gets wider, it's weaker, and that's a plot thickening issue. So that's condition 4, Q straight enough, no outliers, plot doesn't thicken. That is a plot thickening. What do you think is the issue with B? What do you think is the issue with B, Jackson? Don't even look at their answers. Q straight enough, no outliers, plot doesn't thicken. What's the issue with B? Which could be diagnosed with a residual plot 2 or the regular plot. Residual plots are really good for plot thickening, because it's the plot thickening on the residuals. What is the issue with B? Don't even look at their answers. Just think Q straight enough, no outliers, plot doesn't thicken. And look at B. And don't even look at their answers. Just Outlier, boom, Jackson, you got it right there. We're throwing you another 1,000 points. A bad one. Outliers can do anything to regression, so we don't want outliers. So the residual contains, except for the 1 point. So that's talking about the outlier right there. So yes. Now we got a, notice right here, QQ straight enough. That's not a straight enough. It's got outliers and it's got a not straight enough. So there's a curved pattern. It's weird. I wish they also mentioned those weird points. But we have a fan pattern. No, fan looks like this, like it fans out. That's not a fanned pattern. It's not good. It's got a curve. It's got a sad face. I think someone did that as a joke. I'd prefer they just show the nonlinear pattern. But that's a not straight enough right there. But I'm pretty sure someone at Pearson thought it'd be funny to add in a joke. Okay, what do you think about the first one? ABC. So this is the second version of it. Still the same thing. I might just keep this as the same question in the notes. What do you think about the first one here? Don't worry, but think about the first one. A, B, or C? A, B, or C? There's a hint for it. What if all the points are scattered like this right here? So A, B, or C? What do you think about that first one? A, B, or C for the first one right here? So the first one, it's either B or C. Okay, let's take a look. The scatter indicates it's an appropriate regression model, okay? The residual plot indicates that most of the data fall roughly on a straight line with the exception of a single point. So is there any one single point that really deviates? Is there a point on here that really deviates from the model? Like a singular point? Like over here where it looks like a singular point is deviating from the model. Never mind B, you got it right there. Yep, that is actually a pretty good residual plot grade. Oh, we got to throw more points. More points. That is actually a pretty good residual plot. If you look at our theoretical good one over here, sometimes there's a point that's a little further away. So that is actually pretty decent. Don't try to look for one that's a little more obvious like that one. So that would be this next one right here shows the exception of a single point where we have a point right there. And then this one is the model getting weaker or stronger, Blake, on C. So this is a fanned pattern again. Fanned pattern is going to show that it fans out in the residual plot. Please note that this does say residual right here, which is a really great way to tell it's a residual plot. And then is it getting weaker or stronger? So what is happening as the model goes through the data? Is it getting weaker or stronger? Is it getting weaker or stronger? Is the model getting weaker or stronger? What's happening right there? The model is definitely getting wetter. So it's spreading out further away from the line. So the model is getting wetter. It's definitely one of these fan pattern ones, which would indicate the model is getting wetter because it's going further away from the line. And the line is trying to explain the data. So it's definitely getting, is it weaker or stronger? Is it decreasing in power, getting weaker? Or is it increasing power? It's getting weaker, exactly. It's going further away from the line, so it's getting weaker. Good stuff right there. Really good. What should we do next, Blake? Oh, Jackson. Oh my gosh, Jackson. I'm sorry. We've knocked out like 10-ish questions out of like 18. We've done half these, about at least half of these. We still got like 20 more minutes if we want. We can knock out more. Are you feeling good about this stuff, Jackson? Like, good work right here. We're just crushing through this assignment. Just doing them all. We've missed none. I love regression. I teach a whole class on regression. That's how much I love regression. A whole bunch of these. What's the correlation? The table shows the number of line bursts. What if we can do the whole thing? Feeling better? Love that. Table shows the number of line bursts. We did that one earlier. Wait. The table shows the number of line bursts per 1,000 population. Those are easy ones. Is it the number? Oh, here we go. Here we go. This is one I saw earlier. Okay, cool. Let's do it. Table shows the number of line bursts. This is a big one. Okay. This one's going to take a moment. Good stuff right here. Table shows the number of line bursts. Okay. Let's check this out. So with this, what do you think we're going to immediately do with this? What do you think we're immediately going to do with this? Like, we see data like this. What's the best thing to do immediately? When you have data like this for a question, immediately put it where? We're going to go to the button right here, copy to clipboard. Do this layer here, copy to clipboard, jump, yep. So now you notice it has column names. Since it has column names, I'm going to hit Control or Command C. So make sure, sometimes it doesn't pop. You need to make sure they're highlighted. If they're not highlighted, you might have to go to another copy. Like sometimes it has a sub tab. Some questions have that. Some people were saying, wait a minute. Make sure you're on this where they're highlighted in blue. Hit Control or Command C. Now that you've got it in your copy, you need to go over here to Jump. So once you're inside of Jump, go to File, New Data Table. That's File, New Data Table. With File, New Data Table, go ahead and click it. Don't click inside of it yet. I'm not going to click inside of it. I'm just moving it over here. Because now I'm going to go to Edit and then Paste with Column Names. Edit and Paste with Column Names. So now that you've pasted with column names, make sure to paste with column names. It'll appear like this. You could also write it. You could punch the numbers in, make sure they're blue. If they're not blue, you've done it incorrectly. Notice how they are red right here. Did you get? Yeah, we did. We got it at start class. Yo. So if they're red, then you didn't paste them in properly. Just make sure to paste with column names. Don't try to fix it. Just start over and paste with column names. So make sure to paste with column names, and they'll look like this. So now that we have it, I do see a linear. Ooh, wait a minute. It's a negative relationship. Notice how as year is increasing, it's going down. So there is a negative relationship. We can just see that visually. We will solve this using jump, but it looks to me, and that's a previous thing we did. So it looks to me we're either in C or D, because as year is increasing, that's the year since 1900. So they're changing the way it's displayed. They're subtracting. I'm not going to do that. It's either going to be C or D. It's probably D with a little bit of weirdness over there. Analyze fit Y by X. Use the year. Oh, no. Okay. Okay, here's the thing. I think the way they're writing this equation is we need to subtract off the year since 1900. So there's a few ways to do this. I'm going to show you the way to do it without doing formulas and the way to do it with formulas. You can go right here and type in 65, 70, 75, 80, 85, 90. I forgot what comes after that. 95, 100, 105, 110, 115. That solves it right there. You can also right-click a column and jump when you have it open. Right-click it and go to formula. I double-clicked the column right here. You could just type it like I did. This is years since, I double-clicked that, years since 1900. And so that fixes that. You double-click it to change the name of it. You can also right-click a new column and go to formula. So now this opens up the formula builder, and we're just going to go year, and we're going to subtract from it 1900. And then we are going to apply that formula right here, and it's going to solve out the answers for us. So that was right-click, go to formula. When you're inside of formula right here, double-click year, subtract from 1900, and then apply and OK. Either which way, the goal is to get this right here, and you would just want to call this like X variable or something like that. Whatever you want to call it, year since 1900 is the right name, but you can't call two variables the same name. So just make sure you have this column right here, because that's going to come into play in writing the equation. This is just going to help us for doing the math, because the math needs to have that equation written this way. Let's go to Analyze Fit Y by X, and we're going to go years since 1900 is the X, and then we're predicting the rate right here. And let me show that again. I might have went too quick. Analyze Fit Y by X. Analyze Fit Y by X. We're going to use years since 1900 as the X and the rate as the Y variable of interest. And there it is on the screen currently. That's how we do it right there. So with this, let's click OK, and we get our regression model, and it is that one that I thought it would be, that answer D over there. Just looking at it visually, I saw that, really? I think my computer's trolling me. And so with this, we see right here that there is the negative relationship. As year is increasing, we see a decrease, or a little bit of a weird scatter right there. It's mostly linear, except for 2 points that go far away from the model at those years of 1975 and 1990. And so now that is answer D right there. Describe the general trend. It is going to be the birth rate has been decreasing over time. And no, the birth rate is increased. No, each one of these is different for each graphic. Does it go in order? No, it almost does. But this would be random fluctuations. This would be a peak, and this would be increasing. That's decreasing. So they actually do it. Now you have to be careful. We did write our equation properly. Make sure we change the variables, and now we can go here to the analyze fit y by x to get the model right here. So go to the red arrow and click analyze fit y by x. Analyze fit y by x line. Oh my gosh. The red arrow and go to fit line. Now that we have the line fit, we need to know where the intercept is at, which is the first value right here, the B0. And we need to know where the slope is at, which is the second value, negative 0.113. So here is the value of the intercept, round to 2 decimals. And the value of the slope is right here. It's going to be negative. Make sure to take the negative. Is it going to ask us to explain these values? Maybe. There we go. Check to see if the linear model is appropriate to explain. Oof. There's 2 points that kind of deviate. No, because it's nonlinear. I don't see a nonlinear. It's really asking us to analyze this model right here and look at it and say, like, is there a nonlinear? The points mainly go around the line. It's got a little bit of weirdness. I don't see nonlinearity. Outliers. It has to be quantitative to make a scatter plot. D is the only one where I'm a little bit like, we can't run lack of fit. Yes, because the scatter plot shows no scatter plot wouldn't show no lurking variable. Lurking variables are a variable outside the XY relationship, so lurking variables don't apply here, or we'd have to think that through ourselves. Yes, because the outlier is reasonably straight enough, and there are no outliers. Let me look at this. Let me go to, this is the above and beyond. Let me go to studentized residuals. Where's studentized residuals? Save studentized residuals. This is the above and beyond. Yeah, those are not big outliers. Studentized residuals are actually t-scores, which are a lot like z-scores. And so the biggest studentized residual is that value right there. So that standardizes the residual for you. It's basically just a z-score for the residual. Studentized is from the student t distribution. But right here, the negative 2.5 is kind of large, but there's just... See, I'm close on it. It's that point right there, like I said. It's pretty far away, and that's the studentized residual. It's not negative 2.5 below the line. That's it in studentized units, which is a standardized unit of measurement based on t distribution, which is a lot like the z. We'll get into William Gossett later. It's not. I've seen much worse models, so there's no extreme outliers. Don't you do that to me. Don't you tell me there is. Interpret the slope. The slope is for each 1 unit increase in x. We expect y to increase by b1 units. So, no, it's just not. If I got that regression, I'd be super happy. That's a really good regression model. Like, if someone who wrote this question, because this is a new one this semester, if the person who wrote that question thinks that that's an outlier, I'd be like, man, you must have much better regression models than I get, because no regression model is perfect. All models are wrong. Some are useful. So the slope is going to be this right here for each 1 year increase. That is for 1 year. That is correct. For each 1 year increase since 1900, we expect the birth rate to decrease by 0.11 on average. So the number of births in thousands is no. Slope's number, no. For every addition, no. So it is going to be this one. The number of births per 1,000 has been changing by an amount equal to the slope per year on average. That's okay. This didn't go into full description on that. The table gives rates. What? Oh, estimated in the 5, yeah. It's saying it's set to an interval of every 5 years. Predict for 1978. What's really great is if you have your model right here, you can actually go to Save Predicteds. Let me show where that's at. You can go to Save Predicteds right here. Using Save Predicteds, it'll save to your original data table. And you can actually type in 1978, and it didn't put in the value right there. There's the X variable right there. But we have to put this right here because I use that value in 16.72. Now, that's not how you would solve it on the test, but that does help us get the answer. And we can confirm the answer by going back to our regression model and typing in 78 times 0.11. And notice how we've rounded it, which is going to make the answer a little bit different. So all I'm doing is solving that equation, 17.03. So all I did was plug in 1978 right there. So when we do years since 1900, plug in 78 because we're predicting for 1978. And then we get the answer of 1703. 78 times this, subtract from the value, and we get 17.03. In 1978, there was actually this much. So the residual is what right here? So this is really good. I got lost in that. Which one are you lost on right here? The solving. Which part are you lost on? Was it solving the model? Was it solving the model, Jackson, right here on how to solve for that number? Type YRN. Was it to solve for the number? So what is the X value right here? Years since 1900 should be what? So what is the X value right there? So what is the X value right there? What is the X value? Years since 1900, what would be the value of X? Yeah. So with this being make a prediction. So basically the question reads, make a prediction for 1978. Like the question should just say predict for 1978. That's like the easiest way to like state it. Make a prediction for the year 1978. So what should be this value now? What should be that value? Like what should I plug in there? Because that's just a variable. That's just X. Like you could just call this X right here because that's the X variable. So what should that be? When I solve this out mathematically, what should that be? Because it's years since 1978. I mean, years since 1900. 1978 is how many years from 1900? 1978 is how many years from 1900? How many years would it be? 78, yep. And so now what we do is we times this out. Does that make sense right there? Just solve the equation. So what I'm going to do right here is I'm just going to plug in 78 times 0.11, and then I need to subtract that from 25.61. So 25.61, subtract that value right there. Does that make sense, Jackson? So you plug in the value 78 and solve the equation. So since it's a negative right there, so make sure to solve it out. Like there's 25. There go. So when you solve it out, the 0.11 times 78 is 8.58. And so good stuff right there. And so you're doing it. Yeah, I do. You can do it with jump. Jump will solve it for you. But like this one is the one I would suggest not using jump for, like saving predicteds and all that, because that's not very test analogous. So there's some things where I'm like, oh, it's really great using jump because you have to know how to read the output, but you can't use jump to make predictions during the test. So rather than using the jump, you could use it as a backup. Notice how jump is carrying more decimals. I'm a little worried, because there were a lot more decimals on this. We rounded it to 2 digits, and there were some extra decimals, so you would have to subtract more off. So the differences we're seeing, which is like some largeable difference right there. I am interested. We can re-answer the question. I'm a little bit interested to see if using jump we'd get the right answer. So I'd be a little worried using jump actually, because the way they had us round it, we dropped some decimals, which is gonna you don't usually drop decimals till the end, like when you're doing calculations. So, eesh. So we see there was actually this amount. I know, right? So with it being actually this amount, how would we solve for the residual? So remember, this is the actual, and this is the predicted. So what would be the residual? See, you need this number right here. So the model predicted, okay, it's going to predict more. It says round to 1 decimal on that. Oh, no. Oh, my gosh. Blake. Jackson. Oh, my gosh. We got to give you 5,000 points correcting me right there. Thank you so much. That was a correction right there. Round to 1 decimal. So it's really easy. The model predicted 2 more bursts than, I think that's bursts in thousands of units. So they really need, oh no. Oh, Jackson, you know what also? here's the thing too. Phew, I'm about to make multiple errors on this problem because it doesn't want 17. Do you know what it wants? It wants us to take this value right here, and then I believe times this by 1,000 and bring that to units of the problem. No, this is a rate. It's a rate. No, it's per thousand. I'm going to be a little mad if they... I don't know what units they want this in, because they're giving this in units. No, but see, here it's saying 1,000... I'm a little iffy on this problem right now because it's very unclear because it wants you to know the units is in thousands of births, and then it's like switching between... It should say this many births. Birth rate. And then it says births. So estimate what the rate was. Okay, wait, here's the rate. It says rate. That is rate. So that is rate. But then it says this many more births. So I think they want you to know the big thing on this one is also the unit conversion. That one says births and the other one says rates. So I'm pretty sure that's 2,000 because that is estimating 17 births in thousands of units. The other one's saying 15 is the actual. So there's the model predicted 2,000 more births. The residual here would be -2. The birth rate in 2020 was not yet available. Predict the birth rate in 2020. Come on your faith in this prediction. We'll finish off here in a moment. Oh, and then 2050, that's a huge extrapolation down there. So the birth rate in 2020, so mine was... Oh, no, but that would be... So, Mary, you got times the whole thing. So 17.1 times 1,000 is 17,100. So if it was 15, it'd be 2,100. So it'd be 2,100. We'll double check before you hit enter. Make sure I hit enter. Make sure I hit enter. I got to finish up here soon too. I got 4 more minutes till my meeting. So make sure to do that right there. And we answered that one good. So now we need to use the model to make a prediction for 2020. 2020 is 120 years past our model. So now we use the model to make a prediction for 2020. Same sort of deal, just plugging in the value. Make sure to subtract that. 25.61 minus this. There's the value right there, 12.41. And what does it want it rounded to? Round to 1 decimal, so 12.4. Once again, all we did was plug in the value of 120 and solve the model. Exactly. I think Jackson. Sorry, Jackson. I don't know why I'm just saying Blake and... I don't know. It's how to tell Blake and Ethan. I was just saying their names all day today. Come on, your faith. There is some faith. It's not that large of an extrapolation. There is some faith in the predicted value. This is not that large of an extrapolation. It's basically forecasting the future. Predict the birth rate in 2050. So we're going to just plug in 150 again, make a prediction, and this is birth rate. So 150 times 0.11. And then subtract 25.61 minus that, 9.1. Because it wants to round to 1 decimal. This is a large extrapolation. We talked a lot about extrapolation in class today. I had a pretty good talk on that. Extrapolation is going outside the X bounds of the model. And the further you extrapolate, so we were talking about it right here, the more you extrapolate, the more you go outside the X bounds of the data. So comment on your faith here. This is a much larger extrapolation of the model. So I would say... This looks good right here. It's not negative yet. There is no faith. I would say there's little to no faith because extrapolation that far beyond the data is dangerous. Let's check. Oh, what does it say we got wrong? I know we got that right. So let's check right here. Got that one right? Yep. We got this one right. Is it seriously one of the ones on the little tiny rate things? We're just checking each question as we go. Which one? Yeah. Shocked if I got like one of those wrongs. Wow, this was a really long one. Which one? Did I misclick something? I got to type in a value now. Oh, it's this one. No way. It wants 2? Please tell me if you got... That's ridiculous. The birth rate. So that's where if you remember, if you review the video, that's where I was like, what does it want there? Does it want in thousands of units? Because, so Blake, Jackson, oh my gosh. So Jackson, make sure to change that. It's just talking about the residual right there, which is actually -2. So, but the problem is they're talking rates and then they say births. So they should say the model predicts to the birth rate to be this much higher than its true value. So it's still talking about rate right here, which is where I was like, are they talking rate? Because they're talking in units 1,000. So if they're talking bursts, then it's 2,000 more bursts. But they're talking rate. So they're just asking for the residual in terms of rate. So we got everything right. It was just the units thing, but I thought they wanted me to talk about the units. So it's like, do you want the units? You don't want the units. Like, make it clear. It was pretty clear here. Like, estimate what the rate is. Perfect. Here's the rate, and then it should say the rate was off by this much or something. It should say the model overestimates the rate by this, or the model underestimates the rate. That'd be a better way of phrasing this, Mop Pearson. Come on, Mop Pearson, write some better questions for us. So that's some good stuff right there, Jackson. Really good question. Like this, that's what problem is. Like sometimes just maybe not a little bit clear on the wording. That's why I do these things because I don't want people to get tripped up, especially if I can get a little tripped up on their wording. Like, do they want what units? Obviously, we got that one correct because we said 2,000, but it wanted 2 instead of thousands of units. So yeah, it should have said in thousands of units. Could have been a little more clear. Well, with that, we're going to head off right here. Bye for now, everyone. Wait, I was going to change my outro, closing outro. Wait, wrong things. Quick outro. Bye for now, everyone. Bye.